Hello, everybody. Welcome to this short course on quantum computing. So today we're going to start discussing about superconducting qubits. This is a part one. So basically, so far we had talked about qubits and had looked at them strictly from the Hilbert space point of view or the Bloch sphere point of view. However, as we must understand, the qubits do not exist in any mathematical vector space or abstract mathematical vector space, or don't even exist in form of Bloch sphere. These are just visual representations, mathematical representations to make our life easier. So basically, we need some kind of hardware to realize these qubits in the lab. So now we will look into the physical aspect of how a qubit works and what exactly is a qubit, using the intuitive understanding that we had gained while discussing about qubits using vector space notation or the Dirac notation and the Bloch sphere notation. Right? So basically mainly three different qubit technologies exist. One is the semiconductor spin qubits, then we have trapped ion qubits, and then we have superconducting qubits. We'll be focusing primarily on superconducting qubits because they are easy to understand, and even the tech giants like Google and IBM are working on superconducting qubits because of their good scalability property, and also, as I mentioned, easy to understand, easy to make stuffs. So basically, superconducting qubits, basically they are nothing but LC circuits in superconducting environment. So it's obviously more intuitively clearer or easier to understand these things. So we'll be focusing on superconducting qubits for the time being. So what we have in a superconducting qubit is basically makes use of a two-level atom system. So basically in nature, we don't find any two-level atom system as such. However, for the time being, let's assume that we have a two-level atom system, which has discrete energy levels, eigenstates, which are ket0 and ket1. There's a ground state, there's an excited state, and this energy would be h cut omega naught, and this would be h cut omega 1, and the difference delta E would be h cut omega 0, 1. So these are two discrete energy levels, and the system can exist in a superposition of these two states, and prior to and post measurement, it can collapse to either ket1 or ket0. So this is very much similar to what we had discussed in terms of spin. So I think it's not an issue for you to understand this. So yes, now when we have this, we can visualize this in the Hilbert space using a superposition vector, ket psi, and also in the Hilbert, also in the three-dimensional Bloch sphere geometry in terms of theta and phi. So I think this much is clear. Now, what we need to understand is that this ket psi is a function of time. And this functional dependency on time, or the time evolution nature of wave function or the state vector, is given by the Schrodinger equation. This is the Schrodinger equation. So this is a linear first order differential equation, so it's easy to solve. And by solving that, what we have is we get this understanding of the fact that yes, superposition state ket psi is a function of time, is a linear superposition of various basis states. However, this probability amplitude now is a function of time. So the time dependency of ket psi is included in this probability part. So this probability evolves, probability corresponding to each of these eigenstates, right? And this, as you see, is the Hamiltonian, which we had mentioned earlier, is basically the total energy of the system. And just like a spin operator, this is the energy operator. And since now we're talking in terms of energy, so we are using an energy operator. Now, let us assume that this system is not kind of driven by any external source. It's just isolated. It's a free system. In that case, the Hamiltonian becomes time independent. And now this equation becomes very easy to solve. And by solving, we get this. So Cn of t, that is the probability amplitude of the state collapsing to the nth eigenstate as a function of time is equal to Cn at time 0, that is the initial value, times this e to the power minus j En t by h cut. En is basically the energy eigenvalue corresponding to the nth basis state, right? And this can be represented in terms of the frequency of the nth energy level omega n. So what we see is that this is the time evolution nature of the probability amplitude, of the nth probability amplitude. So if I take the magnitude on both sides, what we have is, once we take the magnitude, as you can see, this is a phase term, right? So this term does not affect the probability part. So the phase of the probability amplitude is kind of evolving, and what we can see is that the relative phase would evolve with time, but not the probability. The probability would remain the same as the initial value, and this is the case that we have when we have no external excitation. So now we can express this for a two-level system which has only two eigenstates in terms of ket0 and ket1, right? As you can see, this is the time evolution state vector. This is how it evolves, and this is just a phase relationship. We can take this e to the power minus j omega naught t common, and that would make this e to the power minus j omega 1 minus omega naught t. That would give you the relative phase, but nevertheless, that won't matter your probability of collapsing. However, this relative phase would act like that e to the power j phi of that block vector. So the azimuthal rotation, right? So the relative phase has to do with that. Now, the interesting aspect of this two-level system comes into the picture when you excite it by a time-varying pulse. Time-varying pulse having frequency which is sort of close to the frequency of this energy gap. In that case, the Hamiltonian no longer remains independent of time. It is now time-dependent. There is now a summation of two different Hamiltonians. This Hamiltonian is the free Hamiltonian which we had in the driveless case, and this is the interaction Hamiltonian. So when this electric field I'm looking from classical point of view, and this atom I'm looking from the quantum point of view, when they interact, that interaction Hamiltonian is a function of time, right? And now on solving the time dependent Schrodinger like Hamiltonian and putting that into the Schrodinger equation, the time evolution comes out to this form. So as you can see now, C naught is not just dependent on the initial value, that also evolves along with this phase term that we have. C naught t, C1 t, they also have an individual time varying component in addition to this time varying phase. And this time varying C naught t and C1 t comes due to the external drive, right? So the free Hamiltonian time evolution is captured by this phase terms, and the drive part, the effect of the drive part on the time evolution is represented by this time varying terms. Now, when you have a two-level system, the expression of these time varying terms were found to be oscillating, right? Cos square of something and sine square of something. So what happens is that this omega is a frequency which we call as the Rabi frequency, is a frequency by which this probability amplitudes evolve with time and they oscillate. And this Rabi frequency is proportional to the magnitude of the drive pulse that we had given. And this is the case when we have no detuning, that is the frequency of the incoming microwave pulse matches with the frequency gap of ket0 and ket1. That is when we have this perfect isolations, perfect oscillations, I beg your pardon, and that is called Rabi oscillations, and that frequency is called Rabi frequency. So can you see what's happening over here? When you're driving the two-level atom system with an external drive of some frequency that matches with the frequency of the energy gap of the two-level system, the probability amplitudes oscillate with time, start oscillating with time, right? At a frequency omega, that is a Rabi frequency. So the assumption over here is that the initial probability of occupancy in C naught T square at T equal to 0, that is the probability of occupancy of the ground state at time equal to 0, was 1. This blue color curve shows C naught T, and the same at the excited level was 0. And now look, with time, the probability of occupancy of an electron in the ground state drops sinusoidally, and the same thing increases sinusoidally for the excited state. And then there is this periodicity, and there is this continuous oscillation, and this oscillation will continue once you sort of apply a drive. Now, what we can see over here is that if we apply this pulse, or the pulse width tau is such that omega tau is equal to pi, which is here, then what we see is that once we apply a pulse of this width, so what happened in that case is that this probability of occupancy, which was 1 at the initial point, drops down to 0, and what was 0, that is the probability of occupancy of excited state, that increased to 1. So we are kind of swapping the states, swapping the population of the states, and such a pulse is called a pi pulse. Similarly, if we apply a pi by 2 pulse, that would be here, then what we have is that we create superposition of states. So this is 0.5. So we create we start from here, and then we apply a pulse till here. Then what happens is that the Rabi oscillations will cause the state to reach in this point, where it is a perfect superposition of ket 0 and ket 1. Right? So just try to understand what's happening over here. So I'm able to control the states of my qubit, manipulate it, control it using an external drive. Right? I'm using an external drive of a particular strength that is deciding the Rabi frequency, and of a particular width in time, pulse width, tau, so as to alter the states, making use of Rabi oscillations. So using different kinds of pulses, we can manipulate the qubit in different ways, and that is the core of quantum computing. You have qubits, but you've got to control them. You've got to manipulate them. How do you manipulate them? Is that you have a qubit which essentially works like a 2-level atom, and we send a microwave pulse, and that would swap the states or do something to it, or to create superposition states and different other operations, which would be understood very well once we discuss the quantum gates. This is how quantum computing takes place. So I have an algorithm. I want to reach an optimum state, and I sort of apply a proper architecture in a way to apply or excite the qubits by a proper pulse, so as to obtain the optimum outcome, or whatever outcome I desire. This is how quantum computing happens in a very basic way. Now, as you can see, once we switch off the, once we switch off the driving pulse, these oscillations would die out because of the losses, intrinsic losses that are present in the qubit system. Right? So these oscillations would die out, and we want these oscillations to not die out before the width of the pulse is over. Right? So I need my oscillations to be sustained to a satisfiable period of time, so that I can end my whole quantum operation. And after that, if the oscillations die out, they die out. Then we don't care. However, if we use a very lossy medium, then these oscillations damp out very easily. And that is precisely why we use superconducting materials to realize qubits. Because as we had discussed, in the lecture of superconductivity, we have formation of Cooper pairs, and the conductivity is almost infinity, the resistivity is almost zero, and supercurrent can exist there for a long time. So even the fluxes are trapped in it and quantized. So that is why we use a superconducting material to make a qubit. Now in the next lecture, what we would do is that we would continue from here. We would show that essentially a two-level atom does not exist, but we can artificially make a two-level atom using a superconducting qubit architecture and a hardware, which we would discuss very briefly in the next lecture. So I hope this much is clear to you. So if you are facing a little bit of difficulty in grasping things fast, I suggest that you don't move on immediately to the next lecture. You cool it down, let it cool down for a while, and then rewatch the lecture or look for other stuff present in the internet to gain a better insight of these things, and then move on to the next lecture, right? So thank you very much for watching. I hope to see you in the next lecture. So thank you very much.